Yes, am I audible? Okay.
Yes, sir.
Gautam, you were absent in the last class, huh?
Yes, sir, I was.
Gautam, we just have 2 months now. So try not to miss any class. Okay, so a few new students have joined. Abdullah, Naziha, Sakina, and that's it. Okay, Abdullah, Naziha, Sakina, it's your first class with me, right?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So it's a 2 month crash course. You have 2 months with us, December, January, and maybe some 1 week of February. Yeah. In this around we have 9 weeks, 8 or 9 weeks. You need 8 or 9 weeks, we'll try to finish your complete syllabus. So we are two teachers will teach you. I will be taking the second part of physics, particularly from ray optics, then modern physics, then electronics, and then wave optics. Yeah. And another teacher will be taking electromagnetism. She will be taking your electrostat to AC. So this is how we will try to finish your syllabus in 9 weeks. Uh, in this batch also, you have missed some lectures of ray optics. It's basically third lecture of ray optics, third or maybe second lecture of ray optics. So you have not missed a major portion, just have missed a very minor portion of ray optics. So we just have started the spherical refracting surface in the last class. So I'll give a very brief introduction of spherical refracting surface. And at the end of the class, I'll give you a backup of 20-25 minutes. In that 20-25 minutes, you'll be able to grasp this particular chapter. So this is the last chance to complete full syllabus. If you miss any of the classes or you just take some trial, take it seriously, then it will be very difficult for us to finish your syllabus on time. And there won't be any break for your pre-boards or anything. We have very limited number of hours. Each and every class will be very important. Plus, on every Friday, we have a revision test series. We have already given the schedule. So just try to go through that test series also. And at the end of the class, we'll take a very small Viva type with you so that I could know what is the level of physics. I have to start from the scratch or you have already done some topics. Fine. So we were doing spherical refracting surface in the last class. What is refraction, Nabil? Nabil Ahmed. Nabil. कहाँ भाग जाता है लड़का? Hishma, what is refraction?
Sir, it is the phenomenon of change in path of light.
Yeah. So what happens when a light travels from one medium to another? Due to change in medium, the path of light change, and this change in path of light is known as refraction. Means if light travels from air to glass, then medium changes. Like air is different medium, glass is different medium. Due to change in medium, the lights get refracted. That is refraction. For refraction, few terms are important. The first thing is this angle of this N1 and N2. N1 and N2 are the refractive indices. The refractive indices have same definition as were in class 10th. So N1 and N2 are the refractive indices of two medium. Abdullah, what is the refractive index of air? Abdullah. Nazia, refractive index of air?
3 into 10 raised to minus.
Refractive index, not a speed.
Okay,
What?
sir.
Refractive index. Sakina, you have any idea about the speed of light in vacuum?
Three into 10⁸.
Okay. So I won't ask any question from till the end of the class from you three people. We'll discuss everything at the end of the class. Try to absorb the major portion of this lecture. I'll give you a backup, but at least try to absorb a major portion of this. So we started with the spherical refracting surface. How we obtain a spherical refracting surface? We take a glass sphere. This is a glass sphere, and we cut a portion of the glass sphere. So this portion of the glass sphere behaves as a spherical refracting surface. We also have done how to decide whether the surface is convex or a concave surface. So this is a spherical refracting surface. This particular side is known as the concave side. This side is known as the convex side. We are revising it. We already finished this topic. So if the medium, this is the rarer medium and this is the denser medium. If the surface towards the rarer medium is convex, then we call it a convex refracting surface. And if the medium towards the rarer medium is concave, then we call it as a concave refracting surface. So if you look here carefully, this is the rarer medium. And the surface towards the rarer medium is a convex surface. We call it a convex refracting surface. See this particular example. This is a rarer medium. And the surface towards the rarer medium is a concave surface. So we call it as a concave refracting surface, which is concave towards the rarer. So whether the surface is convex or concave, this decision we take on the basis of the rarer medium. The second thing is the center of curvature. So we cut this spherical refracting surface from this sphere. The center of this sphere is known as center of curvature. So this is the center of curvature. And the separation between the center of curvature and the center of the surface is known as radius of curvature. Or you can say that radius of curvature is radius of this particular sphere, the sphere from which you cut this spherical refracting surface. The center of the surface is known as pole. The separation between the center of curvature and the pole is radius of curvature. Similarly here, the separation between the pole and the center of curvature is the radius of curvature. Then we have discussed the sign convention. The first point in the sign convention is we will measure all distances from the pole. So distances means if you want to measure this distance r, you have two options. You can either start from C and then go to P, or you can start from P and then we'll come to C. So we'll start from P. For all distances, we always start from pole. So we'll starts from pole and come to center of curvature, or we can start from pole and then we come to center of curvature. For measuring any distance, the starting point is always pole. The second is distances in the direction of light are positive. Means if you are going from P to C and light is going in this direction. So Arpit, we are going in the direction of light or an opposite to the direction of light? We are going from P to C and the light is going to the right hand side direction. So in
Sir,
which
in the
direction?
direction of it.
Yeah, we are going in a direction opposite to that of light, right? Light is going to the right hand side and we are going to the left hand side. So in that case, your distance will be negative. If I move from P to C and this is the direction of light, Sakina, we are moving in the direction of light or opposite to the direction of light? I'm going from P to C and the light is also in this direction.
Direction of light.
Direction of light. And when you move in the direction of light, that means the distance is positive.
Okay.
That's a simple sign convention. This is the same convention that you have used in class 10th. Next. So we have two types of spherical surfaces. Your spherical surface could be a convex surface or it could be a concave surface. We can have two types of refraction. One is the refraction from the rarer to the denser medium. Refraction from rarer to denser medium means your object is in rarer medium and your observer is in denser medium. Let's say you are in air and the observer who is observing you is in water. So the object is in rarer medium and the observer is in denser medium. The second case could be the refraction from denser to rarer medium, which means your object is placed in the denser medium and the observer is in the rarer medium. That's denser to rarer. Next, all these refractions can be further divided into two categories. Refraction from rare to denser can be of two types. It could be concave and convex. Similarly, refraction from denser to rarer can also be divided into two types, concave or convex. Means rarer to denser for a concave refracting surface, then rarer to denser for a convex refracting surface. Similarly here, rarer to denser for a denser to rarer for a concave surface and denser to rarer for a convex surface. Then for concave surface, you can have two options. Like you can have two possibilities. You're using a concave surface, but your object, the image that you're obtaining is a real image. Second, your image could be virtual image. So in this concave refracting surface also, you have two cases. You can have a real image or you can have virtual image. Similarly, in convex refracting surface also, you can have two options. You can either have a real image or you can have a virtual image. Similarly here, in concave refracting surface, you can have two options. You can have a real image or a virtual image. Similarly, in convex, you have a real or virtual image. Abdullah, how many total options cases you have? If you just count the number of cases, how many total cases you have?
8.
8 cases, right? So we should have 8 set of formulas. But for all these cases, means all these cases where your refraction is from rarer to denser medium, we can use one set of formula. And again, for all these cases where refraction is from denser to rarer, you can use one set of formula. So for all these 4 cases, one single formula will work. For all these cases, one single formula will work. So we'll have 2 formulas. So let's derive this result. We have already done a portion of this derivation. Let's repeat it again. Refraction from rare to denser medium for convex refracting surface for real image. So you have a convex surface. Where is your object? Akshay, refraction is from rare to denser. Where is your object?
Rare.
Your object is in rarer medium and your observer is in denser medium. Means your image will be in denser medium. So this is the ray diagram. Let's draw the ray diagram again. Let's repeat this entire again. We have finished some part of this derivation in the last class, but it's a very, very important derivations for your board's exams. Very, very important. This derivation along with Lensmaker formula is usually a 5-mark question. So let's first draw the ray diagram. So this is your refracting surface. This is N1. So the type of convention that I use, I always take my rarer medium as N1 and N2 is my denser medium. N2 is my denser. This is the object. This is the pole. And this is the center of curvature. So you have your object is in rarer medium. What type of surface is this, Nabil? Is it a concave surface or a convex surface?
Convex.
Convex. I'll decide whether the surface is convex.
Sir, depending like rare किस तरह.
Rarer. So around towards the rarer medium, you have convex, which is a
Convex.
convex. So let's draw the ray diagram. For the ray diagram, we need 2 rays. First ray is this. This is passing through the pole. So the ray which is passing through the pole will go straight without any deflection. There's no deflection in this ray. It will go straight. Then you have another ray. This is this ray. Incident is ray here. And let's draw a normal. So to decide the angle of refractions incident and angle of refraction, you need a normal. To draw normal on the spherical refracting surfaces, easiest method is join that particular point with the center of curvature. This is the normal. This blue ray is the normal. This is the normal.
So isn't that necessary? We have to draw it in like dotted.
That's your choice. You can either draw dotted or you can draw with different color. The ray should looks different. So the ray, this is the incident ray. This is the incident ray. And this is the normal. So all those students who which have first class with me or someone who have joined after a very long time, just if you can go through, if you can do this derivation, then the entire ray optics will get revised. So this is incident ray, this is normal. The angle between the incident ray and normal is known as angle of incidence. If there is no refraction, then this ray should go straight. This will go straight if there was no refraction. But since medium is changing, you're going from rare to denser medium. So Krishna, if we go from rare to denser medium, what happened to the ray? It will
So
go
rarer to denser means it will bend towards the normal.
Yeah, it will bend towards the normal. So this is the original direction of the ray. This is the normal. Due to refraction, the ray will bend towards the normal. So this is the refracted ray. And this is one ray. This is another ray. When these 2 rays meet, you will get image. So this I is the image. This O is the object. And you can drop a normal here. This is the normal. This angle is angle of incidence. This is refracted ray and this is normal. This angle is known as angle of refraction. Let's call this angle is alpha. Let's call this angle as beta, and let's take this angle as gamma. This is the ray diagram. After ray diagram, let's apply Snell's law here. So let's apply Snell's law. Let's call this particular point as point M. This point where ray gets incident is point M. Now let's apply Snell's law. So, sorry. So let's apply Snell's law. Nazia, do you remember Snell's law? What is Snell's law?
It's a ratio of sine of angle of incident to the sine of angle of reflection. Refraction. Yes.
Is what?
N to 1.
Yeah, N2 by N. And what is N1 and N2? Refractive indices. Yes, Uni, we have not yet completed this derivation, so I'm repeating it. So when we apply Snell's law at M, you can apply Snell's law in product form. So here, the refractive index is N1. The angle of incidence is I, so you can write this as N1 into sine I. If you go into this medium, here refractive index is N2. Angle of refraction is this, this is R. So it's N2 into sine R. So that's my, or we can apply small angle approximation. So when we apply small angle approximation, I can write that sine I is almost equal to I and sine R is almost equal to R. This is small angle approximation. For very small angles, sine I is equal to I, sine R is equal to R. So when you do this thing, you will get N1I is equal to N2R. So that's first equation. Next, what you can do is, you can take some triangle. This is point A. You have to convert this I and R in terms of this angle alpha, this angle beta, and this angle gamma. So for this, you can use this triangle. See this triangle OMC. In OMC, this I is the exterior angle. This exterior angle is equal to the sum of interior opposite angles. You can say that I is equal to alpha plus R, alpha plus gamma. So in triangle, if I name this triangle as OMC, I can say that I is equal to alpha plus gamma. I is alpha plus gamma. That's my equation. Similarly, I have to convert this R also. So if I take this triangle MCI, in MCI, this gamma is the exterior angle. So you can write interior opposite angles is equal to the exterior angle. So you can say in triangle CMI, you can say that gamma is it's R plus beta. Or you can say that R is it's gamma minus beta. Let's call this as equation number 3. So we have I, we have R. We can substitute this value of I and R here. So let's substitute equation number 2 and equation number 3 in 1. So when you do the substitution, it's N1I, which is alpha plus gamma, is N2R, which is gamma minus beta. This is the equation number 4. The next task is to convert this alpha, gamma, and beta in terms of the side of the triangle. So for this, we can use some more triangles. Is it clear up to here? Akshay, Saifullah, Minashi,
Yes, sir.
Yes, sir.
Sakina?
Yes, sir.
Okay. Next is to convert this angle in terms of sides. So we can do that using this triangle. Let's take triangle MNO. In triangle MNO. If I take this triangle MNO, in this triangle, I can write that tan alpha is,
Mn upon
this is MNO. So tan alpha will be Mn by NO. Tan alpha is Mn by NO. Let's call this as equation number 5. Next, we can write tan beta also. So for tan beta, I'm using this triangle MNI. In triangle MNI. This is M, this is N, and this is I. So tan beta is again perpendicular upon this base. You can write this tan beta is approximately equal to beta, which is equal to its Mn divided by Ni. Let's call this as equation number 6. Gamma. Let's take this triangle MNC. And triangle MNC. Tan gamma is approximately equal to gamma, which is equal to its Mn by I. Not Mn by Ni, Mn by Nc. I'm taking this triangle MNC. So here this is gamma is Mn perpendicular divided by Nc, which is base. Let's call this as equation number 7. Next, what we can do is we can substitute 6, 7, and 5 in 4. Substitute 5, 6, 7 in 4. We can substitute all these three equations in equation number 4. When we do these substitutions, we have N1, which is alpha plus gamma. Alpha is Mn divided by NO plus gamma, which is Mn divided by Nc, which is equal to N2 gamma. Gamma is Mn divided by Nc minus beta, and beta is this Mn by Ni. So Mn by Nc minus beta here. Beta is Mn by Ni. So Abdullah, can you see any term is getting cancelled from the left hand side and right hand side?
Mn, sir.
Mn, yes. You can take Mn as common, it will get cancelled out. Huh? So Mn get cancelled out from both the sides. So simply this Mn, this Mn, this Mn, this Mn gets cancelled out. Mn gets cancelled out. You have N1 divided by NO. I'm multiplying with N1 here. N1 by Nc is equal to its N2 by Nc minus N2 by, I'm sorry, I did some mistake. This is gamma. Gamma is Nc, and this is beta, which is Ni.
Ni.
This is Ni. Let's call this as equation number 8. Now the last step of the derivation. Now we'll use an approximation which says that aperture is small. Aperture is small. Aperture is very, very small. Aperture is small. See, if the aperture is small, aperture means this size of the surface. The size of the surface is very small. If size of the surface is very small, then you can write simply that P and N is very, very close. P is pole. We should take all distances from poles. So we can say that P and N, these 2 points are very close. If these 2 points are very close, then you can write all distances which we are taking from N, NC, NO, NI in terms of P. So P is close to N, which means NO can be written as PO, which is equal to. What is O? O is object. What should be PO? Object distance. We usually represents object distance by U. Similarly here, what is C? Radius of center of curvature. What is this distance? Radius of curvature. This I is the image. From P to I, this is image distance P. So this is object distance U. This is image distance V, and this is what we call the radius of curvature. So if you look at this figure carefully, what is PO? That's U. It's plus U or minus U?
Sir, it would be negative.
You're going in the direction of light or opposite to the direction of light? See, light is going to the right hand side and you are going from P to O. This is opposite to the direction of light, so it should be minus of U. Similarly, NC would be PC. What is PC here, Anshika? Anshika. Anshika Takran, what is PC? ये बहुत गलत बात है अंशिका, गायब हो जाती है बीच में।
Sir, it is R.
हाँ, it is R. इतना लैग क्यों होता है? PC is R. प्लस R और माइनस R अंशिका? PC is plus R or minus R? Plus R. You're going in the direction of light, huh? PC is plus R. The next is Ni, which is equal to Pi. And how much is Pi? When you're going from P to I, this is plus P. Let's call this whole as equation number 9. So we can substitute all values of 9 in 8. So when you substitute all these values, you get N1 by NO. NO is minus U. N1 by NC, which is R, which is N2 by NC, which is R, minus N2 by Ni, which is V. So when we simplify it, so what we can do is we can take this V to the left hand side, we can take all terms carrying R to the right hand side. So we can write this as N1 by minus U plus N2 by V is equal to, I'm taking this N1 to the right hand side. Huh? So you have N2 by R minus N. So you can write this as N1 by minus U plus N2 by V is N2 minus N1 divided by R. So this is the required formula for the spherical refracting surface. And this is a general formula. General formula means this is valid for all type of surfaces, all cases. So you should use sign convention when you use this formula. This is one thing. So this is the formula that we're supposed to derive. This is the formula for the spherical refracting surface. And see, this is valid for all cases, like all cases of rare to denser. So if your refraction is from rare to denser, whether your surface is convex or your surface is concave, this formula is valid. Whether your image is real or your image is virtual, this formula is. For numericals, this is that we will be using. This N1 is rarer medium and N2 is denser. This is how I derive this thing. So whenever I derive this expression, I always take N1 as rarer, N2 is denser. So it's fixed. Even for numerical, this is fixed. So in numericals, denser would be our N2 and rarer would be our N1. Okay, do one thing. Let's don't copy this derivation. Just please take the screenshot. To save some 10-20 minutes. Let's take screenshot of it, please.
Sir, I have a doubt.
Yes, Arpit.
So what
So we
is
have to follow sign convention.
Yes, we have to solve sign
Putting the values.
numericals. Yes,
Okay.
when you use these values in numericals, you have to use sign convention again. Yes, Arpit, you're saying something.
Sir, I was asking like what if it falls from denser to rare?
Then we'll derive it again. Second derivation. Next derivation is for denser to rarer. The only difference will be instead of 1, you will have 2 and 2 will have 1. Okay, I'm sharing a link of this notebook in the chat room. So take screenshot, or if you want, you can just go through the link also. So where is the chat room? Chat room. So I shared the link of this notebook. This link have all chapters. Chapter 1, notes of all chapters. Chapter 1, 2, 3 optics.
So when we will start the lens with the formula?
Hmm?
Because sir, I have my exam day after today, so I have a doubt in it.
Arpit, your voice is not very clear. Echo रहा है, बहुत ज़्यादा. Just take screenshot, please. Don't just write this derivation. Take screenshot. See, this is the type of derivation that you will not use this calculation in any numerical. There are certain derivations where you use steps in numericals also, but you won't be using any step in numericals. Just take screenshot. You can write this after the class. We'll save time. You can save some time. I believe you have taken the screenshot. Just take screenshot of this portion also. Now, please take screenshot of this portion. So this is the formula for refraction from rarer to denser medium. Then you can derive another formula for refraction from denser to rarer medium. Means your object is in denser medium, your image is in rarer medium. Up with lens maker formula, I don't think I can start today. We'll do lens maker formula in the next class. But I can give you lectures on recorded lectures of lens maker formula from the last year. Okay. The next is this refraction from denser to rarer medium for a concave refracting surface. Now there's a second type of derivation where instead of rare to denser, you have denser to rarer. Abdullah, what does denser to rarer means? Where is the object? Your object is in denser medium or in rarer medium? Abdullah, what does denser to rarer means? Your object is in denser medium or it's in rarer medium?
Sir, object is in rarer, I think.
When you say refraction is from denser to rarer, that means your object is in denser medium and your observer is in rarer medium. This is what we mean by denser to rarer. So denser to rarer means object is in denser medium and your observer is in rarer medium. Now let's draw the ray diagram. Okay, let's draw the ray diagram. So we start with a concave surface now. On the last derivation we did with the convex surface, now we'll take a concave surface. So this is N1, which is the rarer medium. And this is N2, which is the denser medium. So you should at least know these two sets of derivation, refraction from rare to denser and then refraction from denser to rarer. So denser to rarer means, Sakina, where is your object, denser or rarer medium?
Denser medium.
Denser.
Your object is in denser medium. Let's put your object in denser medium. Abdullah, are you still in class? This is center of curvature and this is the normal. Okay. So this is your incident ray. If there is no refraction, then this ray should go in this way. But your refraction is from denser to rarer medium. Krishna, what happens when your ray travels from denser to rarer? It bends towards the normal, it bends away from the normal. Away from the normal. So instead of going in this way, this will go away from the normal here. And one ray is going through the pole. The ray going through the pole is going straight. It will not have occur any refraction. So this ray and this ray. These are converging rays or diverging rays? Noah. Noah, these two rays are converging or diverging? Noah. Nazia, these two rays are converging or diverging?
Diverging, sir.
Diverging rays. So diverging rays never makes a real image. They won't meet anywhere. So to get an image, what you will do is you will just produce this ray in the backward direction. When you produce this ray in the backward direction, it appears to meet here. So that is your image. So this is your image. So this is your object. This is the normal. And this is your image. So Nabil, is it a real image or a virtual image? This eye. Nabil Ahmed, is this a real image or a virtual image?
No.
This
Virtual
eye,
image.
virtual image. See, the rays are not actually meeting. You're just producing these rays to meet at some point, a virtual image. This is an incident ray. This is a normal. This angle here is known as angle of incidence. This is your refracted ray. This is your normal. This angle here is known as your angle of refraction. And this is your angle alpha. This is your angle beta. This is your angle gamma. And let's drop a perpendicular. Let's name this point as M and let's name this point as N. Do one thing, draw this ray diagram first, then we'll start the calculation. Draw this ray diagram first. So we take a different type of surface. We take a concave surface, so we're taking virtual image, the case where you get a virtual image. Just tell me once you have done with this ray diagram. Just draw the ray diagram, then we'll repeat the calculations. Saifullah, Miraj, is it clear? All calculations.
Yes, sir.
Yes, sir.
Minashi, any issue?
No, sir, clear.
Uneeb, problem with ray diagram?
Yes, sir.
Any problem with this ray diagram?
No, sir.
Tell me once you are done
Done,
with this
sir.
ray diagram. Done. Can I scroll? Sakina, Nazia, Anshika.
Yes, sir.
Akshay?
Yes, sir.
Sure. After this ray diagram, we have to repeat all steps. So I will not write. I will just repeat this thing. So let's start with the Snell's law. Here, the angle of refraction is N2 and the refractive index is N2, angle of incidence is I. So you can write N2 into sine I is N1 here. Medium is N1. Angle is R. So it's N1 into sine R. Then what you can use small angle approximation. When you use small angle approximation, you can write sine I equal to I and sine R equal to R. So that's your first equation. N2I is N1R. Next, what you can do is you can, in triangle OMC, you can, you have to relate this alpha, beta and gamma with I and R. So see, in triangle OMC, which one is the exterior angle, Nabil? OMC, which one is the exterior angle?
Sir, I.
I is the exterior angle. See, OMC, this I is the exterior angle. So you can write that I is alpha plus gamma. So I is the exterior angle. You can write this as alpha plus gamma. If we take another triangle, like if I take triangle IMC, in IMC, this R is the exterior angle. So you can write that beta plus gamma is equal to R. Next, you can substitute 2 and 3 in 1. When you do the substitution, instead of I, you will have alpha plus gamma. Instead of R, you will have beta plus gamma. This is the equation. Then the next step is you have to connect this alpha, beta, and gamma with the sides, for which we use standard triangles. OMN will give alpha. So what is tan alpha? Tan alpha is perpendicular, which is MN, by base, which is NO. Similarly, what is tan beta? Tan beta is Mn by Ni. Tan gamma, what is tan gamma? It's Mn by Nc. So you have alpha, beta, and gamma. You can substitute the values of alpha, beta, and gamma here. Instead of this gamma, you can write Mn by Nc. Instead of this alpha, you can write Mn by No. Instead of this gamma, Mn by Nc, Mn by Ni. Mn gets cancelled out. N2 by Nc, N2 by No, N1 by Nc plus N1 by Ni. Now you can write this in terms of object distance and image distance. Again, N and P, these 2 points are very, very close. If the 2 points are very close, that means all distances that we have calculated through N can be written in terms of P also. So we can write P and N are very close. So you can write NC, which is equal to PC equal to plus R. NO, you can write this as minus U. NI, you can write as minus V. See, this P to C is R. Huh? This is the radius of curvature. P to O is your object distance. So you're going from P to O, opposite to the direction of light, so it's negative. P to I is your image distance V. You're again going from P to I, opposite to the direction of light, so it's negative again. So when you substitute all these terms here, means instead of this NC, I'm writing R. Instead of NO, I'm writing minus U. Instead of NC, I'm writing R again. Instead of NI, I'm writing minus V. So when you do all these substitutions, you get this expression. So if you compare this expression with the one that we have derived from the rarer to denser medium, Anshika, can you compare these two expressions? What was the difference between these two expressions? The expression that we have derived for that surface, rarer to denser medium, and this for denser to rarer. What is the difference between these two expressions? Anshika. Anshika, I'm waiting. Relate these two expressions, the expression that we have derived from rarer to denser and this expression for denser to rarer. Okay, Anshika will not do. Yashika, can you relate these two expressions? One from rarer to denser and another from denser to rarer? Yashika. Uneeb, can you relate these two expressions? One from rarer to denser and another from denser to rarer?
सर पिछले वाले मैंने एंड रिजल्ट लिखा नहीं था लास्ट में.
So the end
Sir,
result.
this is negative of the.
Not exactly negative, Nabil. There is a difference of 1 and 2. This was earlier was N2 by U, N1 by U, and this is N2 by minus U. So in the first expression, if you replace 1 and 2, like instead of 1, you write 2, instead of 2, you write 1, then you get this expression. See, the earlier was, and for rarer to denser, the expression was N1 by minus U plus N2 by V is N1, N2 minus N1 by R. So see, earlier you have N1, you have N2 now. Earlier you had N2, now you have N1. N1 minus N2, you had N2 minus N2. So if you remember the formula for rarer to denser medium, then just replace N1 by N2 and N2 by N1, and you will get formula for denser to rarer. So these are the two important derivations that one should know. Just do it fast. Just do these derivations very fast. Note it down. So it's 9:19. I'm giving you 4 minutes to write, 5 minutes to write this derivation. Do it fast. Then we'll do numericals of this thing, and we will try to start Lensmaker formula. Sorry, Arpit.
So I am asking like which is the most important topic in the chapter, because I have my exam. So like what's the most probable कि numerical आ ही सकता है उधर से.
This is TIR.
Okay.
Then that apparent depth thing, then spherical refracting surface and lens maker formula. You'll get definite derivation or numericals on this thing, lens maker formula.
So we can get the derivation of lens maker formula too.
Yes, super important.
Oh.
Lens maker formula is super important.
So
What's
can
the
you tell,
syllabus? What's the syllabus?
sir, ray and wave? Sir, it's a 40 marks test.
40 mark. Wave is already over, so in ray. Okay. Okay, I'll try to let's see if we can finish lens maker formula today. Let's see if we can finish it.
So, but in the application, say diamond and mirage is like deleted, right?
But you should know those things. You should know those things. And they don't take much time. Written? Can I scroll it now? Noah? Only Krishna, can I scroll it now?
1 minute, sir.
Nabil, I have to discuss something with you. So let's have a call at the end of the class, huh? A WhatsApp call or a IMO call or something.
Yes, sir.
Sakina and Nazia, written?
Yes, sir.
Yes.
Is there Nazia or Nazia?
Naziha, sir.
Nazia.
So can you give a numerical based on this topic?
Will do. It's okay, not on this. And remember, these are general relations, so one should use sign convention over here. There's one interesting thing also, like if you derive these expressions instead of N1 and N2, if you take incident and refracted medium, then you will see that both the results are same in terms of incident and refracted medium. So I'm not going to that type of convention where instead of rarer and denser, we take incident and refracted medium. So if you do these calculations in terms of incident and refracted medium, then in both the cases you will get same result. So there are few authors who write this formula in terms of incident medium and refracted medium. So they don't have two formulas. They don't have two separate formulas. They have just one single formula. Written, Akshay, Arpit.
Yes, sir.
Yes, sir. Done.
Okay, the type of numericals that you get on spherical refracting surface can be classified into two categories. The one is where you have a single refraction. there is only one single refraction. Then you have another type of numericals when you have two refractions. So this is the easier one. You have a single refraction. So in this numerical, you just have to decide whether your refraction is from rare to denser or your refraction is from denser to rarer. Note down this question, draw a rough sketch, and write down in the chat room whether this is the refraction from rare to denser or denser to rarer. I'm the co-host. Huh? I'm not host. I'm the co-host. So in chat room, just send messages to me. Just write down the question, draw a rough sketch, and tell me whether the refraction is from rarer to denser or it is from denser to rarer. Okay. Apit is correct. Noah is correct. Yashika is correct. What about the rest? Just read the question and tell me whether the refraction is rare to denser or denser to rare. Easy thing. Yes, Nabil is also correct. Just check where is your object. If your object is in rarer medium and your observer is in denser medium, then it's rare to denser. Otherwise, it's denser to rarer. Krishna, Miraj, Nazia, Alia. Krishna is correct. Akshay is correct. Sakina is correct. Oh, Krishna. Write down your answer. Yes, rare to denser. It's correct. Fine. So almost everyone is right. It's a rarer to denser medium, right? So, and what type of surface is this? In air falls on a convex spherical refracting surface. Huh? So this is the convex surface. So this is air, a rarer medium, and this is glass denser medium. So you can check towards the rarer medium, you have convex with a convex surface. This is your object. So your object is in rarer medium and your observer is in denser medium. So the question says that light from a point source in air falls on a convex spherical glass surface, mu is 1.5. So the refractive index of glass is 1.5 and that of air is 1. So Nazia, which one is N1? What is N1 here? It's 1 or 1.5?
Sir, it's the rarer one.
So which one is the rarer one?
The
Air is
air.
the rarer one. So your object is in rarer medium, your observer is in denser medium, so the refraction is from rarer to denser. So the formula that we will be using is the refraction from. See, in numericals of ray optics, it's compulsory to draw the ray diagram. Huh? If you don't draw the ray diagram, then this is of no use. You won't get full marks if you don't draw the ray diagram. So the refraction is from rarer to denser. So if refraction is from rarer to denser, then we're using this relation n1 by minus u plus it's n2 by v is n2 minus n1 divided by r. So Nazia, what is n1 here?
Air 1.
1. N2 is glass, denser medium, 1.5. What is object distance here? Object distance, Miraj. How much is object distance? Mehraj.
120.
120?
No,
we
it's
take,
100.
we take all distances from pole. Plus 100 or minus 100? Sign convention is important, Miraj. Plus 100 or minus 100?
So plus.
Plus 100. See, the light is going to the right hand side. Huh? For measure distance, you will start from pole. When you start from pole and go up to O, so you're going in the direction of light or opposite to the direction of light?
Opposite.
So your object distance will be opposite, minus 100 centimeter. Image distance, you're going from P to C, so you're going in the direction of light. So when you go in the direction of light, it's positive, it's plus 20 centimeter. Just substitute the values. N1 is 1.
Sir, should we convert
Sorry.
centimeters to meter?
No need to convert. Sorry, that's not image distance. Image distance is that we have to calculate. P to C, what is the distance between P to C? R. So it will be positive or negative?
Positive.
You're going in the direction of light, so your R is positive, it's plus 20 centimeters. No need to convert in meter. You can keep all your calculations in centimeters. It's not an issue. So when you substitute values, N1 is 1, U is minus 100, so it's minus of minus 100, plus N2, which is 1.5, divided by V is unknown, N2 minus N1, 1.5 minus 1 by R, which is 20. So that's 1 by 100 is 1 by 100 plus 1.5 by V is 0.5 by 20. So you can write 1.5 by V is 0.5 by 20 minus 1 by 100. So it's a straight calculation. So this is 1.5 by V. When you take LCM here, it's 100. 20 by 5, 0.5 into 5, it's 2.5 minus 1. So you have 1.5 by V is 1.5 by 100. Gets cancelled out. Your V comes out to be 100 centimeter. Object distance and image distances are equal. Okay, it can happen. Yes, is it clear?
Yes, sir.
Nabil, Yashika, issues?
Yes.
Clear, sir.
It's okay, note it down. We'll do another numerical. So this was the easy type of question. You have a single diffraction only. But you can have double diffractions also. Like there could be another surface, so light could. So if you want to complete the ray diagram, this is your image. This is your image. And what is the image distance? That is again 100 centimeter. If you want, I can repeat this numerical again. Krishna, Arpit, Sakina, is it clear?
No, sir, it's clear.
Okay.
Yes, sir.
Great. Next numerical will be a bit more involved. That will have two surfaces. We'll have two refractions.
Sir, ये convex है concave?
See, this is air. Towards air, you have convex. There's a convex refracting surface. Just check from the rarer medium. If towards the rarer medium, you have convex with a convex surface. If you have towards the rarer medium, you have concave, then it's a concave refracting surface. Note it down, we'll do one more question. Okay, I've shared assignment of this spherical refracting surface on the group also. So just practice these questions after the class, and if you have doubt, we can discuss them. So just 4 questions on spherical refracting surface. Okay, can I scroll it? Let's do this question. No, just straightforward. Let's do one question. Do question number 3. Question number 3. At least draw the ray diagram. We'll do it together, but at least draw the ray diagram.
Sir, the globe is made up of glass.
Yes.
Okay.
Okay, it's 9:37. You have 3 minutes. Try to solve it and write your answer in chat. First, draw the ray diagram. Without ray diagram, you can't solve these numericals. Hmm?
Sir, here we have to find object distance or image distance, sir.
Image distance. Object distance you have now. Your rays are coming parallel to the axis. So you have object distance. You have to find image distance. And image distance is also from the center of the sphere, not from the pole. Just 2 more minutes you have. Answers. One more minute. Okay. Nabil gets some answer. Yashika, your answer?
Sir, I'm calculating.
Okay, Noha. Akshay, Nabil, Noha, you all are getting the same answer, but I think it's wrong. It's not the correct answer. No. No, Akshay, not even infinity. Yashika, you are writing something or should I start calculations? Okay, Uneep. What about the rest? Saifullah, Hishma, Minashi.
Almost done, sir.
Okay. Sakina, Mazia. Answers. अरे ओके मुनीब अरे भाई ट्राई तो किया करो गलत होगा कोई बात ओके नोहा नाउ इट सीम्स करेक्ट नाउ यू आर करेक्ट ओके सैफुल्लाह okay मुनीब okay let's start this calculation sir. So sunshine recorded globe of 30 centimeter diameter, so the diameter is 30. How much is radius of curvature? Radius of curvature will be
15 centimeter.
The correct answer is 7.5, not 45. So 45 is a very common mistake. See, so the ray enters the globe parallel to the axis. So the rays are parallel. These are the parallel rays. So you have to decide where these parallel rays are converging. So that is the first surface. This will be the refraction. So this is the pole of the first surface, P1. This is the center of curvature. What type of surface is this, Ishma? This surface. The convex or a
convex.
concave surface? Yeah, it's a convex surface. Sorry, towards air it's convex. What type of refraction is towards the first media, first surface, Sakina? The refraction is from rarer to denser or denser to rarer?
Rarer to denser.
Rarer to denser. So the refraction is from rarer to denser. So if the refraction is from rarer to denser medium, then you can write this equation, no? N1 by minus U plus N2 by V. Minashi, again, it's not the exact answer. It's N2 minus N. You are missing something. So what is N1? N1 is always the rarer medium, right? So N1 is 1. N2 is always the denser medium, which is glass, which is 1.5 given. What is U? Your rays are parallel. Parallel rays come from infinity, so U is infinite. V you are supposed to calculate. R is the radius of curvature. See, you are going from pole to center of curvature. You're going in the direction of light. So radius of curvature will be plus 15 centimeter.
सर मैंने तो यू को इन्फिनिटी रखा था मेरा तब भी
बता रहा हूँ क्या गड़बड़ की है. N1 is 1, U is infinite, N2 is 1.5, V is V, N2 is 1.5, N1 is 1, then R. So you have 1.5 by V is 0.5 by R. R is how much is R? It's 15. So when you cancel it, it's 5, 3, 30, no? When you multiply it, V comes out to be 45. See, it's not the final image. It's not the final image. See, it's 45 centimeter. Yes, rays are converging in 45 centimeter. Now let's complete the ray diagram. These rays will refract and will try to converge at 45. This is 30. So they will go outside the globe. When they go outside the globe, then these rays will refract again. See, these are the rays, huh? Let me take see, this is the new thing in this numerical. This is the modification. If there is no refraction, then ray will go straight. And you can say, yes, this is the image. The image is at 45 centimeter. But tell me, can this ray go straight without any refraction? It will refract again.
Sir, it will refract.
It will refract, sir.
It will refract again. This is the catch in this numerical. There's two refractions, so this ray will refract again. It will not go straight. It can't go straight. This is the second refraction with this ray undergo. If there is no refraction, then it should meet here. This is the second refraction. So, Hishma, for this second surface, the refraction is from denser to rarer, or it's rarer to denser?
Denser to rarer.
Yeah, it's first refraction. Next we have denser to rarer. Second refraction we have to calculate. Denser to rarer. Now again, there is another point which can confuse you. For the second refraction, what is the object? For this second surface, refraction for the second surface, what is the object? For the first surface, you were saying that object is at infinity. Yeah? Your object was at infinity, and this I is the image. But for the second surface, what is the object? Object is the image. The image of first surface will act as an object for the second surface. So what is object for the second surface? For the second surface, object is this I. This I is the object. So you can say this I is the object for second surface. And what is the object distance? See, this is pole P2. What is the object distance? This is the object distance. See, from P1 to I, the whole is 45. This is 30. So how much is this? 15. This is your object distance. Is it clear? The image of the first
Yes, sir.
surface is acting like an object for the second surface. It's 15. Is it plus 15 or minus 15? See, you'll measure from pole now. When you start from pole and you travel up to this
Yes.
I, you're going in the direction of light. If you're going in the direction of light, then it's positive plus 50. Yes, it's plus 50. So U is plus 50. Second surface, U is plus 15. Okay, what is R for the second surface? For the second surface, you're going from P to C. You're not going in the direction of light. You're going in a direction opposite to that of light. So your radius of curvature is negative. V we have to calculate. N1 is always the rarer medium one. N2 is always the denser medium, which is N1.5. Okay, so Saifullah, which formula will use here? Just tell me the formula. Which formula will use here? Where is Saifullah?
N1 by V minus N2 by U equals to N1 minus N2 by R.
N2 by minus U plus N1 by V is N1 minus N2 by R. Let's substitute all values here. When you do all substitutions, N2 is 1.5, U is minus 15, N1 is 1, V is supposed to calculate, N1 is 1, N2 is 1.5, R is 15. So this will go, so we have, this is 15 and 115. You divide, you get minus 1 by 10, plus 1 by V.
And so R is minus 15, right?
R is, yeah, thank you, minus 15. So 1 in minus 1.5 is minus of 0.5 divided by minus 15. So minus gets cancelled out, just 5, 150. So you have minus 1 by 10 plus 1 by V is 1 by 30. So 1 by V is 1 by 30 plus 1 by 10. So 1 by V is 30. It's 1 plus 3, which is 4 by 30. So V is 30 by 4. So V is 7.5 centimeter. But this 7.5 centimeter is from P2. So this ray will again refract and will converge somewhat here. And this separation is 7.5 centimeter. This is from P2, but it's asking you to calculate from the center of curvature. Is asking you to calculate from the center of curvature. Yes. So from the center of curvature, this entire distance will be 7.5 plus 15, right? 15 plus 7.5. So that's 22.5 centimeters. So this is the distance from the center of curvature to that point. That's 22.5 centimeters. Is it clear? Nabil, Akshay?
Yes, sir.
Note it down. Draw the ray
Yes,
diagram. Ray diagram is important. Don't miss ray diagram. Ray diagram.
Sir, can you please share the video lecture of lens maker formula?
Yeah. So if you go to that channel, this Learnivio channel, and if you type in video lectures, lens maker formula, Azam physics, you'll find something. What lecture पढ़े हैं आपने? Yes, Akshay.
I'll get it from there.
I'll tell Saurabh to share with you. Asking Saurabh to share. Can I scroll it?
Yes, sir.
So that was spherical refracting surface. The next topic is lenses. So let's start with. Gautam, clear?
Yes, sir.
Okay. So after this, let's start with the lenses. So that refraction for spherical refracting. So the next is lenses. So everyone have written up to here? Nabil, Noha, Sakina, Akshay.
Yes.
Yes, sir.
Okay. Let's start with lens. Okay, so what is lens? Lens is the combination of two spherical refracting surface. So you can have we have studied three types of refracting surface: convex refracting surface, concave refracting surface, and a plane refracting surface. So you can combine any two type of surface, you can get a lens. So if you combine two convex refracting surface, you get a convex lens. If you combine two concave refracting surface, you get a double concave lens, a biconcave. You have this lens also. One is
So your voice is lagging.
plane, another is convex. You have plane. Now, look at these two lenses, the last two lenses, then you will say that there is no difference between these two lenses. Right? I just reversed the first lens and I got the second lens. I just changed the orientation and I got the second lens. So to differentiate between first this convexo-concave or concavo-convex, you have to calculate the focal length. That we will study in lens maker formula. So if the focal length comes out to be negative, then it's a concave lens. If the focal length comes out to be positive, then it's a convex lens. So you should remember these things, right? Okay, sorry. I'm repeating again. Am I audible now? No?
Yes, sir.
Okay. So
Can
lens,
you repeat from the start?
yes, I'm repeating it again. Lens is the combination of two spherical refracting surface. If both the surfaces are convex, then we get convex lens. Like in the first example, this surface is convex and this surface is always also convex. You get a double convex lens and a biconvex lens. This is concave, this is also concave. Both the surfaces are concave, so double concave lens or biconcave lens. One is plane, another is convex, you get a plano-convex lens. One is plane, another is concave, you get a plano-concave lens. One is convex, another is concave, then you can name it as concavo, convexo-concave, or you can write this as concavo-convex. This lens is convexo-concave if focal length is negative. This lens is concavo-convex if focal length is positive. Basically, if you look at these two lenses, they are not two different lenses. Just take this lens and change its orientation. You will get this lens. Palat kar rakh do, you will get this lens. So how will you differentiate whether this is a convexo-concave or concavo-convex by the focal length? If focal length is negative, then this is convex or concave. If focal length is positive, then this is concave or convex. And how will you decide whether the focal length is positive or negative? That you will decide on the basis of Lensmaker formula. Just apply Lensmaker formula. That's it. Note it down. Akshay, Lensmaker formula is very, very easy. If it's just you have to apply spherical refracting surface twice. That's it, and you'll get a Lensmaker formula. It's very, very easy. So in the next class, we'll hopefully finish this thing.
Sir, can you scroll up a little bit?
Yes. Yes, written everyone.
Yes, sir.
Okay, so let's
Yes,
stop
sir.
here.
No, 1 minute, sir.
Yes. So the major portion of this chapter is over. Now we have just this Lensmaker formula and we have lens formula. Then this refraction is over. Then we'll start with the optical instrument.
Yes, sir, done.
Okay. So let's stop. We'll continue this in the next class. Okay, if you have any doubts, I can discuss them or you can leave. Naziha and Sakina, please wait. I have to discuss something.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
Thank you.
Okay.
Thank you, sir.